So hello everyone, this is lecture 37 for the mathematical physics. In the last lecture we were discussing about some real functions in the complex domain, and we were seeing that how they relate, means how they are in the real and how they are in the domain of the complex. Okay, so in the last lecture we completed about the exponential function. We did up to here. In the today's lecture we will see trigonometric functions and the hyperbolic functions. So first let me give you a basic idea what is the difference between these two. Okay, so only I will give you which is required for your exam and for your understanding only. Okay, we won't go into very much detail. So trigonometric ratios are defined on a circle. You know that on a unit circle you can define all the ratios, whereas the hyperbolic functions are defined on the hyperbola. Means you will have something like this kind, this kind curve or this kind. Then these are the symmetry axes. Here these are the symmetry axes. So that's how these two curves differ, and the functions defined on this we represent by them sin h or cos h. Means all trigonometric ratios with that hyperbolic comes from here. Okay, and normal functions comes from here. So we'll see that how these two are in the complex domain, and I will tell you more about these in the real values also. So first we already defined this, the exponential function in the complex domain, that was exponential ix is nothing but cos x plus iota sin x, and exponential minus ix will be cos x minus iota sin x, because minus will give you minus here. Now this is a two variable equation, x plus y and x minus y. From here you can find the value of cos x and sin x in terms of exponential value. Okay, just try to find them. Means subtract this equation from this equation, you will get for sin x, and add these two equations, you will get for cos x. So you will get cos x equal to this exponential ix plus exponential minus ix divided by 2, and sin x will be this exponential ix minus exponential minus ix divided by 2 iota. So these are the values you will get. So that's how we define cos x and sin x in terms of exponential. So this is very simple thing. Now this is in the real cases. Okay, now what happened in the complex? So it's just same. Okay, it's just same. So it's again a natural extension of real to the complex. Cos z will be, just repeat this formula in place of x, write z. So exponential iz plus exponential minus iz divided by 2, and sin z will be same. Okay, so you need to remember these results, these are very important. And tan z will be simple sin z by cos z, cot z will be cos z by sin z. First we are studying about the only trigonometric functions, how they are represented in the complex domain. So sec z will be 1 upon cos z, cosec z will be 1 upon sin z. Simple ratios, if you remember the trigonometric functions, so you can remember them easily. Now the second property is exponential z, cos z, sin z are entire functions. Means in complex domain also these functions are means differentiable at all points, and that's why we call them entire function, which means analytic at all points in the complex plane. So remember, these functions are analytic at all planes, and tan z and sec z are analytic functions except when cos z is 0, because you can write it as sin z by cos z 1 upon cos z. So cos z equal to 0 will make it diverge. So that's why for only exception for these values they will be analytic at all points. Same for cot z and cosec z. For cot z will be cos z over sin z 1 upon sin z. So for sin z equal to 0 they will diverge. That's why only remaining those points where sin z equal to 0 we will have these functions as analytic. Okay, now let's see the differentiation for the trigonometric functions. So it's just same. Cos z will give you minus sin z will give you cos z, tan z will give you sec square z, and you can verify these results also. See, you need to find the derivative of cos z. So cos z is this, so differentiate this. Exponential iz will give you exponential iz and I again, and here you will get minus iota, exponential minus iota z. Now you will have, take the iota common, and you will multiply with iota, so you will get just difference of this, and you will get something like this with minus sign. So that will be minus sin z. Try to solve this, find the derivative of this, you will get this with minus sign. And if you differentiate this, you will get this one direct. So you can verify these results. So they will be same. Cos z will be minus sin z, and sin z will be cos z. Tan z will give you sec square z. And we know how exponential iz can be written. This is the Euler's formula. You know that cos z plus iota sin z. So remember this. So these all results are very important. Just to make them notes. Okay. So real and imaginary part of cos z and sin z. Now let's see if z is x plus iota y, then how we can define cos z and sin z. Okay, because now cos x plus iota y should be expanded, so you should remember these formulas. If z is x plus iota y, then cos z will be cos x cos hy cos hyperbolic y minus iota sin x sin hyperbolic y. So how you can remember these formulas? These are just simple. Take z as a plus b. A is x, b is iota y. So cos a plus b is nothing but cos a cos b minus sin a sin b. And this sin a plus b is sin a cos b plus cos a sin b. Now you need to remember this thing when you write this. Cos x cos y. So there will be some identities. See, cos iota y will always be cos hyperbolic y. Sin iota y will be equal to iota sin hyperbolic y. Cos hyperbolic square y minus sin hyperbolic y square y equal to 1, and this sum is cos hyperbolic 2y. So it's just opposite what we have for the real functions, means what we have for the normal circle functions, trigonometric functions exactly. So there we get cos square x minus sin square x as cos 2x, and cos square x plus sin square x is 1. It's just reverse. Here cos hyperbolic square y minus sin hyperbolic square y is 1, and plus will give you cos hyperbolic 2y. So you need to remember these identities, very important. Using this you can directly use the formula a plus b, and when you get cos iota y, you can write directly cos hyperbolic y. And when you get this minus sin x sin iota y, so you can directly write iota sin hyperbolic y. Okay, so that's how you can remember these formulas, just a simple expansion. Now if cos z, let's see these results from here also, means how we can verify this result, this one. So cos z is nothing but from here 1/2 exponential iz plus exponential minus iota z. So write it as it is. Now we will write in place of z x plus iota y. So here it is. Now take the iota x, iota minus iota x, and this iota I square y, means to take the terms common. See, exponential iota will multiply inside, so iota x, then iota square y, then exponential means to separate these two, so you will get exponential I square y will give you exponential minus y, and exponential iota x will give you cos x plus iota sin x using Euler's identity. Same here, you will get iota minus I square y, so it will give you iota y, and exponential y, and exponential minus iota x will give you cos x minus iota sin x using Euler's identity. Okay, now just see these. Take the cos x common. With multiplication you will get exponential minus y plus exponential y, and take this 2 inside, so you will get this. And taking the iota sin x common, you will get exponential y minus exponential minus y divided by 2, and this is nothing but this cos hyperbolic y, and this is sin hyperbolic y. Okay, so this is the definition actually, that this is defined as this, means if there was iota here, iota y or minus iota y, then you will get only cos y. When there is no iota, then you will get simple cos hyperbolic y, and here also. So you need to remember these things very important. Okay, so, and this is this, so we get formula for cos z as cos x cos hyperbolic y minus iota sin x sin hyperbolic y. Same you can prove this for here also. Okay, so remember these identities, very important for the hyperbolic functions. Now let's see some more things. So this is our cos z. So cos z, this is our identity. Okay, so cos z square mod square can be written as cos square x plus sin hyperbolic square y, and sin z mod square can be written as sin square x plus sin hyperbolic square y. So you need to remember these identities. Let's prove one, then you can prove second likewise. So cos z mod square, From here, cos z is this. This is our real component, this is our imaginary component. So mod of cos z will be under root square of this plus square of this, and again square will cancel out the square root, so you will get these terms. Okay, now you can write cos hyperbolic square y as 1 plus sin hyperbolic square y from using this relation, this third one. Now this, so multiply this inside, so you will get cos square x sin hyperbolic square y, then this term. So this second and third term will give you, take sin hyperbolic square y common, then cos square x plus sin square x. This will be 1. So you will get mod of cos z whole square is equal to cos square x plus sin hyperbolic square y. So that's how we proved this. Same likewise you can prove this second also using this sin z. Okay. Now let's see if these functions are periodic or not. So cos z and sin z are periodic with period 2 pi. So you can see this easily. Cos z are nothing but these. So if you will increase x by 2 pi, so see x plus 2 pi will give you again the same equation. Here also with 2 pi you will get the same equation, but with y it will tending to infinity, so it will be periodic in x. So we will get the period 2 pi, and mod x we know this lies between 0 and 1, and sin x lies between 0 and 1. This is the real functions, we know that. Cos z and sin z are unbounded because when y tends to infinity, means the real functions are bounded between 0 and 1, the circle equation, remember. But the complex function of the trigonometry, okay, so they tends to infinity as y tends to infinity, because only x is periodic but y is hyperbolic. Okay, so it will go to the infinity if y tends to infinity. You know, from here you can see that they are not bound. So they are unbounded. So cos z and sin z tends to infinity. So this is the difference. Means we talk the similarities, and we have seen that what are the similarities between the real functions of the trigonometry and the complex functions. But now there is a difference also, that they are bound but they are unbound. Okay, and there is limit, there is no limit. So remember these differences also. Now let's see some examples. Means if cos z is given and we need to find z, then how you can find that? So if cos z equal to 0, then see from here, mod of cos z is this. So if cos z mod is 0, then this should be 0 and this should be 0 separately. Only then this equation will be verified. Okay, so we will write cos x equal to 0 and sin hyperbolic y equal to 0, then find the value of z. So z is x plus iota y, and cos z equal to 0 will give us cos x equal to 0 and sin hyperbolic y equal to 0. So this can be 0 for x equal to 2n plus 1 pi by 2. So for all these values this will give us 0. From n can be 0, 1, 2 and 3, and it can be anything. And but the sin hyperbolic y will be 0 only for y equal to 0. So we are getting x as this and y as this, and z is x plus iota y. So with cos z equal to 0, z will be plus minus this 1 upon 2, 2n plus 1 pi, and plus 0 iota. Okay, because y is 0, so I didn't write it here. So z will be simply this. For all these values you will get cos z equal to 0. So that's how you can find. See, if sin z equal to 0 was given, then how you can find the z? Then sin z equal to 0 means sin x should be 0 and sin hyperbolic y should be 0. So sin x can be 0 only for all the values, for x equal to plus minus n pi, 0, 1, 2, 3, 4, minus 1, 0, 1, 2, 3. For all these values sin x will be 0 and sin hyperbolic y will be 0 for y equal to 0. So and our z will be x plus iota y. So x is this and y is 0, so z will be plus minus n pi plus 0 iota, so I didn't write it. So this will be your z. So that's how you can find the z from the trigonometric functions. You need to remember these results. Now let's see something complex. That was easy, the previous one. So if cos z equal to 5 is given, we need to find the z. So z is x plus iota y, and cos z can be written like this: exponential iz plus exponential minus iz divided by 2. Now see, this can be converted into a quadratic equation. How? 1 upon this 2 will go this side, 10, and 1 upon exponential z will give you exponential 2z plus 1 divided by exponential iz. So take exponential iz as x, so it will give you x square plus 1 divided by means it will give you, yes, x square plus 1 divided by x equal to 10. So you will get this, means now this equation we put exponential iz as x, okay, or a. So it will be a square minus 10a plus 1 equal to 0. After solving for exponential iz means a, you will get these values. So exponential iz is this. Now see, if we write in place of z x plus iota y, so it will be like this, means x plus iota y will give you exponential iota x, and iota square y will give you minus y, and the value of this is real, means there is no imaginary term. So exponential iota x will be 1 because it can't be 0. Exponential iota x, the power of exponential can't be, means this value of exponential x can't be 0. So we can simplify this to this form, and this is this, and these both are real, so only these values refer to this value, and this will be 1. Okay, so we put this as this. Taking log, or we can see that for x equal to all the values of 2 and pi, we will get this value. How you can see that? Exponential iota x is nothing but cos theta cos x plus iota sin x. So this will be 1 for cos x equal to 1. So cos x equal to 1 for x equal to plus minus 2 and pi. So that's how you can find this x equal to plus minus 2 and pi. So n will be 0, 1, 2, 3, anything. So this will be our x. So we already get our x. Now we need to find the y. So y you can find from here. Now this should be equal to these, because this is a real value, and iota with this, so we already solved this. Now for this equal to this, you can find y from here. So take the log, so you will get y will be plus minus 2.292. So that's how. Now you have x, you have y, so z will be x plus iota y. So x is this plus minus 2 and pi plus minus 2.292 iota. So this is your z. That's how you can find for anything. Now see, you can find for this also, means you need to solve this cos x plus iota y. So how you can solve? Just use the identity cos x cos hyperbolic y, cos x cos y minus sin x sin y, then use the other identities and you will get this equation. Means you can directly use this identity, this one, and you will get this value. So these are all are in radians, so you can find the values, and this will be this. Now see, remember this identity also. Cos z1 plus minus z2 will be cos x, means cos z1 cos z2 minus plus, means these are simple as we already discussed in the trigonometry, sin x plus y sin x minus y. So these are the same results, just you need to remember these. And cos square z plus sin square z equal to 1, as simple. And cos hyperbolic z can be written this. I already told you, if there is iota then it will be normal cos z, when there is no iota it will be hyperbolic z, same as sin hyperbolic z for also. And now if you find the derivative of this ez will give you ez again, e minus z will give you minus ez minus e to the power minus ez. So you will get again this value. Differentiating this, you will get this value. So differentiation of cos as hyperbolic z will give you sin hyperbolic z. So you can prove this relation. And differentiation of this will give you this, so this will give you this. So these are the same results, but here they are different, means in the normal function cos x was given as minus sin x, but here it is the same, no negative sign. Okay, and these are also same. Tan hyperbolic z is nothing but sin hyperbolic z divided by cos hyperbolic z. For cot it will be cos divided by sin, sec 1 by cos, and cosec 1 by sin for hyperbolic also. And you can see here now, as I told you, cos hyperbolic z is this, so in place of z here is iz, so write iz here in place of z. So you will get exponential iz plus exponential minus iz. So this is nothing but cos z. So you can see that cos hyperbolic iz is nothing but cos z. So that's how you can prove this. Same in place of z, write iota z. So you will get this relation. So this will be equal to iota sin z. So this is the proof I was talking about, where it was cos hyperbolic iy equal to cos y. In the previous, I have given you these relations to you. So that's how you can prove them. Now cos I z is equal to cos hyperbolic z. Remember these relations. Means this also can be proved. Same likewise. Because you know what is cos theta. Cos theta you can write in the form of iota. Then in the place of theta write the iota z. So you will get again this equation. So using these formulas and the previous ones for cos z and sin z, you can prove all these relations and all the derivatives. So these are very important, means these two and the simple ones cos z and sin z with iota. These four relations are very important. All the relations are depending on them. So remember these results. Sin iota z is iota sin hyperbolic z and iota sin I z, means these are the proof of this. So remember these relations. Now remember these relation also for hyperbolic z1 plus z2 you will get, means there will be no negative sign now. These all signs, all trigonometric ratios will be in the hyperbolic ratio, and you can find the analogy to remember these results. Not very much hard to remember. Now let's see the logarithmic function in the complex domain. If z is given x plus iota y, then we need to find the w, which is log z. So what is the value of w? Means we need to find the log z. So from here we can write z as exponential w. So see, this can never be 0 because this is power of exponential. So this can never be 0. That's why we can say that z equal to 0 is not defined. Means the 0 inside the log is not defined because this can't be 0 ever. So that is the reason for that. Now, and this also can't be negative. So this can't be negative. So remember these results. These are the same as we discussed in the real domain. Now let's find the value of w. So w is log z, and let's say that w is u plus iota v. So we need to find the u and v value. So if z is x plus iota y, so it can be written in the form of r e to the power I theta. So this is polar form. So z is ew from here, and so r e I theta will be equal to e to the power u plus iota v, because w is this. So we just related this, and w is this. So now from here we can write it as eu multiply e to the power iota v. So from here eu will be r and v will be theta. So we get already, means we need to find the u and v, and now we have u and v, because from here you will take log both sides. So log r will give you u. So you have u and theta is v. So right, w will be u plus iota v. So log z, this is w, this is u, and this is v, iota v. So this log r is nothing but, means r is nothing but mod of z, and this theta is nothing but argument of z. So log of z is nothing but this. So remember this relation. This is very important relation. Now we can write it in many forms. Means this is because r is mod z, so you can write theta is argument z. Now argument of z is not a single value, it's a principal value and the 2n pi, because remember it is periodic. So you can get infinite value of arguments, but the principal range is this argument z. So this argument z is this. So log z equal to log mod z plus this original principal value plus 2n pi iota. So there are infinite values possible for this function. For log z will be infinite values because of infinite values of argument. Okay. Now see, we can separate this term and this term, and this is called the principal value. Okay, because this is single valued, means the value of this is single value, and this will give us infinite values. Okay, so this is called the principal value, and we can write this as capital ln z. Now principal value is this ln z. Remember, if it is asked in the question that find the principal value, so you will find this. Okay, now let's check for z equal to x. If z is x, then what will be the log z? So it is x plus 0 iota y. So this is a real function, so argument z is 0. We can see that argument of this is 0, so argument z is 0, so it will be ln z will be ln x. So this is a real, so from here we can see that this is a real function. So there is only one value possible, that is ln mod z. So it verifies the real results we are getting for the log, real natural logarithm. So that's all for today. If you have still having any doubt, I tried my best to resolve all the issues or the make the good understanding. Otherwise you can put it in the comment section. I will try to resolve them again. Thank you.